review of what we did with linear motion. We have velocity, which describes a change in position over time. So like how fast something is moving and in what direction. That's going to be a key for all of these. We have a magnitude and a direction. So there is a position that changes in a certain direction divided by the time. Velocity. Great. Momentum describes the motion of an object even more thoroughly than velocity, because velocity might tell us how fast it's moving and where. Like we've said a bunch of times, there's a big difference between a golf ball moving 5 meters per second north and a garbage truck doing the same. So we want something that encapsulates the motion, how much momentum it carries. If it hits you, what will the difference be? Is the way that I like to think about it. So momentum, just multiply the velocity by the mass. So it's also a vector, points in the same direction as velocity. It just has this scaling factor now, the mass. And finally, how do we change our momenta? Well, we apply forces over time, and more specifically net forces. So the net force acting on an object multiplied by this delta p. So again, F net and delta p are in the same direction. We're just scaling this net force by some amount of time to determine how big the effect is on the change in momentum. So forces applied over time cause a change in momentum. Great. So what else is there besides all these linear quantities? Well, there's a rotational analog for each one. And just like for x and y in linear systems, where we can talk about the x direction and do our whole problem, momentum conservation, forces, everything in that direction, separately for the y, and then put them back together, we can do the same thing when we look at one system with the rotational and the linear pieces of it. So if we think about a ball rolling down a hill, this is a system so far the linear piece of it we could describe just fine, right? We have some object with a mass that is moving down a hill with some momentum, and over time, gravity is applying a force that increases this object's momentum. Right? This actually involves acceleration, so it's a step beyond. We'll get to that later in the quarter. But at the end of the day, it's just an object moving, and its motion is changing because of forces acting on it. Great. But we also know if it's a ball, there will be this additional element of something going on, an additional physical phenomenon to describe, which is that the ball rolls. It starts to rotate. And over time, we know that as it speeds up, as its linear motion increases, it will start to rotate faster. And that carries with it there's a velocity we can describe, an angular velocity, there's a rotational momentum, and there's also a torque that we can talk about. So we'll get into what all that means, but at the end of the day, that's another split we can make between linear and rotational motion in systems. So let's talk about the angular rotational analogs of these linear quantities. So velocity, we have, unsurprisingly, angular velocity. Except now, instead of a change in position over time, I have a change in angle over time. So instead of how fast am I moving, it's how fast am I rotating. And all of these will have vector quantities, just like our original linear quantities did. We'll have to do a little more work, we'll get to that, on how we actually decide what the direction is. But how do we know that we need a direction? Well, if I told you all to rotate 90 degrees, you have a bunch of different choices, right? You can rotate one way, you can rotate the other, you can be part of a backflip. Saying 90 degrees, just the magnitude is not enough. So just like with linear, we need magnitude and direction. So that's our velocity, angular velocity. How fast are we rotating and in what direction? Then we have an angular momentum as well. We know how fast something's rotating, but not all things rotating at the same velocity, angular velocity, are going to behave the same way. Just like different objects moving with the same speed with different masses carry different momenta, different objects with the different, called rotational inertia, this value I, carry different amounts of rotational momentum, angular momentum, right? If I spin this chair, or if I spin a carousel, both with the same angular velocity, so let's say it takes both of them 30 seconds to go in a circle, which one do you think carries more angular momentum? Probably the carousel. We haven't talked about why yet, how to calculate it, but you can get this feeling that the amount of motion how hard is it to stop a carousel from rotating? How hard is it to rotate a carousel? That's a lot more than it is to rotate this chair. And that will have to do with their, like I said, rotational inertia, which we will learn how to calculate. And just to go over, I guess I didn't mention these actual letters here. Angular velocity is omega. It's like kind of just like, it's a curly W, I like to think of it. Theta is an angle. So here our curly omega, our angular velocity, is brought into our equation for angular momentum. Like I said, by multiplying our new rotational mass, this I is rotational inertia, moment of inertia is another word for it. Multiply those together, we get L, our angular velocity. Again, that's a vector as well, same direction. Our angular momentum is in the same direction as our angular velocity, right? Because we're just scaling by this rotational mass. And then finally, how do we change our angular velocity? How do we get a delta L? Well, we apply a rotational force, or a torque. And we'll learn how to calculate that too. But same thing, whatever direction my net torque is, my net rotational force will be the direction of my change in angular velocity. So these equations follow the same kind of relationships between each other, and they apply, like we can apply the same method of thinking, where again, like things like F net is all that matters, right? If we have two equal and opposite forces acting on an object, yes, there's forces acting on it, but the net is zero, so there's no change in momentum. Same deal here, many torques acting on an object, but if the net is zero, if they all add up to zero, there's no change in angular momentum. So once we learn how to calculate and understand what these new quantities are, the problem solving that we already developed will be very useful. All right, so each of these is a vector. We need a magnitude and a direction. So how do we describe them? Magnitude is easy. We've already done a lot of describing the magnitude of angles. We just use degrees and radians, right? 90 degrees, 180 degrees. Those correspond to pi over 2 and pi. If you're not comfortable with radians, that's something to brush up on. YouTube video, Google images of like a sheet. Or I mean, this describes everything here. But the most important thing to know is that one complete rotation, 360 degrees, is 2 pi radians. Another key thing to know is radians. Yeah, question? What did you just say about the 2 pi radians? Yep, one full rotation, so like 360 degrees, is 2 pi radians. So radians are unitless. So we'll see what that means in a sec. But when if I plug in 2 pi in an equation, radians isn't an actual unit, like meters or seconds or something. It's just a quantity. So we'll see how that comes into play. All right, magnitude's easy. How do we describe the direction of all these angular quantities? Right, like I mentioned, if I said rotate 90 degrees, there's a lot of different choices that you could make. But how do I quantitatively describe what that is in a way that is, we want two things. We want it to be the same for all observers, right? We don't want it to depend on the direction that we're facing. And we also want it to be consistent over time. So what's one way we commonly describe rotations, just in everyday conversation? We say counterclockwise, clockwise, right? But that's not so useful if we want this first thing. We want it to be the same for all observers. Well, why? Let's take a look. Sorry if you're listening to this on YouTube, but if I rotate my hand, you can try this yourself, I guess, rotate my hand, to me, this is clockwise, right? What direction would you describe this to be? Counterclockwise, right? That's no good, because if we're trying to evaluate a physical system, we don't want to get different answers, have different ways of talking about it, just because you are sitting facing this wall and I'm facing that wall, right? So counterclockwise and clockwise are no good because they depend on where you're observing from. What about like a normal, like left, right, up, down, something like that? So let's talk about, right now, I'm going to rotate my hand again, like above my head, just move my arm in a circle, and let's try to describe the angular velocity of my hand. Well, right now, it's at the top, and it's moving for me to the right, and you to the left. So already that's no good, because it's different for all of us. But also, the other reason that's not good is because now I wait a sec, and now my hand is horizontal, now it's moving down for me, and U. Now it's moving left for me, right for you. So not only is it not consistent for all observers, it's inconsistent over time, right? We want, if my hand is just going in a circle at a constant angular velocity, we want to describe that with one direction, and that's no good. So you should have seen this in DL a bit, but we're going to use the right-hand rule. The right-hand rule is just, it's just a physical way for us to take advantage and always get a consistent answer, but it turns out to be the one unique direct. We could use the left-hand rule too if we all agreed on it, but we're going to all agree on the right-hand rule. So this is a decision. So let me back up a second. The choice we have to make is to use the axis that is perpendicular to the axis of rotation. So if we were describing the angular velocity of my hand right now, the only axis that makes sense, that's not changing over time, and that could be consistent for everyone, is the one that's perpendicular to that. So it would be toward me, or toward you, in and out of the page, if you want to think about that, if I was rotating in a circle on the page. Whether, which side is positive and which side is negative, that's a choice. Us as physicists, mathematicians, whatever, we use what's called a right-handed coordinate system. What does that mean? It just means that we use the right-hand rule instead of the left-hand rule. There's nothing physically, there's no universal law, fundamental in nature, that says the right hand is the one that decides which way is positive, which way is negative for rotations. That's just a choice. But since we all agreed on that choice, just like we all agreed that when we're doing electric circuits, we talk about the flow of positive charge for whatever reason, use your right hand. So, yeah, well, I'll make that mistake a lot. I often just end up using my left hand by accident. I get the wrong answer. So maybe glue your hand shut. That's a great method to use on a quiz or sit on it, something, but just make sure you're using your right hand. Anyway, what is the right hand rule after all of that? Well, you wrap your fingers. You should have tried this a little in DL, but you should curl your fingers of your right hand with the direction of a rotation, and your thumb will then point in the direction of the angular velocity, angular momentum. Right? So let's try it with this chair like I just did, rotating it this way. We should all get up. I encourage you to try these yourselves. No matter where we're sitting, this angular velocity of a chair rotating is up. And then, if I were to reverse the motion, we should all get down. So now we've done two things. Well, I guess we've checked 3 boxes. 1, we all agree. 2, it's constant in time, right? No matter where in its rotation this chair was, the direction that the right-hand rule spits out is the same. And then finally, what we just discovered here was that reversing the rotation flipped the sign, right? We went from up to down, which is also good, right? When we do the opposite thing, we want to just slap a negative on there. So this ends up being a good system. And we're going to use it for changes in angle, theta. We're going to use it for angular velocity, omega, curly W. We can use it for angular momentum, and torque. So right-hand rule is very important. And the way we write about it, because often the systems we'll see will be happening on the page, something like a wheel rotating on the page, something like that, or often we'll need to use the z direction, into and out of the page, in addition to this x and y. And so the notation into is this little cross in a circle, and out of is a little dot. The way I was taught is if you think of an arrow traveling into the page, you'll see the feathers, you'll see the cross, and if an arrow is traveling toward you out of the page, you'll see the point. But those will be our vector notation. Instead of writing north or something like that, you might write into the page. Okay, so let's just do a quick check of it. Use your right-hand rule here. Cars moving in the direction marked this way. Which direction do the angular velocity vectors of the wheels point? All right, I'm going to stop us there. So if this car is traveling, now I'm standing here, we would not, yeah, so the car is moving in the positive x direction. The wheels are going to be rotating like this, so the tops are moving forward and the bottoms are moving backward, right? If we curl our fingers in the direction of that turn of the wheel, we get into the page. And that's true for all four wheels. All four wheels are rotating in the same direction, so they should have the same angular velocity vector direction. And that would be into the page. Yeah, question on that? Can everyone agree that that's what we would get? Okay. Okay, so now let's apply this to each specific unit. We'll just go through with in more detail. So angular velocity, like we said, it describes the speed at which something's rotating and the direction. So we have to describe it with a change in angle over a change in time. So delta theta over delta t, where theta is the angle. This example on the bottom right just shows here's my delta theta, this angle opening up. So if we're all looking at this board, we would say counterclockwise, but that's no good because someone sitting on the other side of the board looking at it would say clockwise. So our angular velocity vector that we would assign to this, and also the delta theta vector, we curl our fingers, we get out of the page, right? So we get an angular velocity and a delta theta that are out of the page for this example. The units of angular velocity are just inverse seconds. Because like I said, radians are unitless. So delta theta, theta, they're all measured in radians now. So make sure you are not necessarily permanently switch, but make sure you're paying attention to what your calculator is set to, degrees or radians. But radians divided by seconds is just inverse seconds. Radians doesn't actually carry a quantity, and we'll see why that all works together for our quantities later on. But that's angular velocity. So let's do a practice question with this. What is the angular velocity of, and I should say the hour hand of an analog clock? So it takes 12 hours to complete one full rotation. What is the angular velocity of that hand in seconds? So I'll give you a sec to do the calculation, and I accidentally quit iClicker. I'm just gonna, there you go. What is the angular velocity of the hour hand on an analog clock? Question? What did you say? Oh, there you go. Yeah, I had it on the old one. All right, about 20 more seconds. All right. So how do we calculate angular velocity? We divide a change in angle by the change in time. How fast is it rotating? How long does it take to complete some rotation? So what are the easiest number to select here, I guess, since we know it's the hour hand, would be we know that it completes one full rotation in 12 hours, right? So our delta theta is one full rotation, which would be how many radians? 2 pi radians. And our delta t, our time, like we said, is 12 hours. but I asked for the units of my angular velocity to be inverse seconds, so I have to change the hours into seconds. 12 hours times 60 minutes per hour times 60 seconds per minute. And then finally, I asked for not just the angular speed, but the angular velocity. So I need a direction, and we should all agree from our right-hand rule that this hour hand is going to be moving with an angular velocity that is into the page. And so the answer is A, this 0.000145 inverse seconds. We could have chosen any other interval too, right? I said like it takes 12 hours to go 2 pi around, but we should get the same answer if I said, well, it takes 3 hours to go pi over 2, right? 1/4 of the rotation takes 3 hours. And so we would get just the same answer because we would have this over 4, this over 4, get the same thing. If we wanted to get the angular velocity of the minute hand maybe, then it would just be this times 60, just because every time the hour hand goes around, the minute hand does so 60 times. Is that true? No. Every time the hour hand goes around, goes 1 hour, let's say it that way. Every time the hour hand moves 1 hour, the minute hand moves around once. So it would be times 12, right? Well, I think I got that right in lecture A. There's no recording of it, so we'll never know. But you should be able to do the same calculation. But hopefully this just helps you get a feel for that an angular velocity is just a change in an angle divided by a change in time. All right, so angular momentum. Once we have the angular velocity of something, how do we actually describe that motion a little better? How do we know how hard it is to stop that object that's rotating, or how do we know how hard it is to give that amount of angular velocity to an object? We need the rotational mass, or rotational inertia. Another word, moment of inertia. These are all things that mean the same thing, but it's our analog of mass for rotational problems. We'll talk about how to calculate it later on, but for now, just know that it's like our analog of mass. It just tells us, gives us how much, from an angular velocity, what angular momentum does an object carry? That's what I is. And it's just a scalar, right? So we take our angular velocity omega, multiply it by some number, I, and we get a vector, our angular momentum, that's in the same direction as our angular velocity, just like momentum is in the same direction as velocity, but scaled by this mass type of thing. So same little diagram I drew on the previous slide, except now I say this object has a moment of inertia I, doesn't matter what it is, but some moment of inertia. So now our delta theta is out of the page, our angular velocity omega is out of the page as well, and our angular momentum is just either the angular velocity times I, so that's also out of the page. So delta theta, omega, and angular momentum L all point in the same direction. So now let's calculate what this angular rotational mass, moment of inertia, rotational inertia is the most common. I think rotational inertia is probably the most common vocab used in like DL and FNT, but rotational inertia, moment of inertia are both interchangeable. Rotational mass isn't really used much, but it's a good way to think about it. Okay, so this formula here, we've seen this sigma before, it just means a sum. We're adding up this quantity, mr squared, for each of the mass elements. So if we were being like really precise, it's an integral, like if we would use calculus to add up little pieces. But you can just think of it as every object is made up of a bunch of little chunks of mass. Maybe think of it just like made up of atoms. So we just have to add up the contribution of each one of those chunks of mass to the moment of inertia, and then we can calculate it. And the thing that comes into play here is r, the distance from the axis of rotation. So it's not just the amount of mass that we have that matters, it's the configuration. How far away is this mass from the axis of rotation? And so that tells us two things. One, like I just said, it depends on the geometry of the object, but it depends on the axis of rotation, right? So if I wanted to figure out the moment of inertia of this chair, there's a bunch of mass distributed all around, right? There's some in the arm here, there's some in the back, some in the seat, whatever. And if I am spinning it around the center point right here, all those pieces have a defined distance from the center, from the axis of rotation, right? So that could be one way to calculate it. But then what if I rotated this chair like around me in circles like this? The same chair, it's the same mass total, but now all these different mass elements of this chair have a different distance from the axis of rotation because we're using a different axis of rotation. So moment of inertia depends on the configuration of the mass and the axis of rotation, and it acts as our rotational mass. It tells us how much angular momentum an object carries. So let's do some examples to calculate it. So in this case, we only have one mass element. We just have a mass m, and it's rotating around this point. So our axis of rotation is this point, a distance r away. It's like a ball swinging in a circle on a string, maybe. So here our sum is just one element. It's just the mass of the object times its distance from the axis of rotation squared. So here I is just mr squared. That's the simplest it can be. What if we were to double that mass? So now we still only have one mass element to sum over. Same distance away, but it's twice as heavy. So now our moment of inertia is 2mr squared. So we found if we double the amount of mass in a certain spot, it has twice the contribution to a moment of inertia. Which that kind of makes sense, right? If we have two objects that look exactly the same, but one's twice as heavy, like twice as dense, we would assume the heavier one is going to be harder to rotate, harder to stop from rotating. Pretty intuitive. What if we have one mass element that's the same as the original mass, just m, but it's 2r away? So we double the distance it is away from the axis of rotation. In that case, we still only have one to add up, but this 2r gets squared. So its moment of inertia is actually 4mr squared. So if we double the mass, if we have just one element, we double the mass, we double the rotational inertia. But if we double the distance of that mass from the axis of rotation, we quadruple it. Now that's not a relationship you need to memorize, but it's important to know that the moment of inertia is very sensitive to the configuration of the mass. Something that's very light can have a significant moment of inertia if that mass is distributed far away from the axis of rotation. This is something I think you'll do an example with in DL where you have this bar with mass distributed around it, and where you rotate it from, like the center point, greatly affects how hard it is to rotate, which is actually pretty similar to this next example. So now we have our first one where we actually have to do a sum. Now we have two mass elements here, and so we need two terms. We're going to sum up the mr squared for both, and they both have a mass m and a distance from the center of, or distance from the axis of rotation of r over 2. So we get mr squared over 4 plus mr squared over 4, or the final being mr squared over 2. So now, remember in our original case when we just had one mass m and distance r away, we had a moment of inertia mr squared. And now we have half that, despite the fact that we have double the mass. So that's just, again, driving home that the choice of the center, the axis of rotation, is very important, because here we have twice the mass as we had before, but half the moment of inertia. So just because something is heavier doesn't mean it has necessarily a higher rotational inertia. And for instance, what if we pick that anchor point to be same object now, two masses a distance r apart, but instead of rotating them from the center, we rotate it from the center of one of the masses. Now in our sum, that one that's centered around the axis of rotation has an r of 0, right? There's no distance from that mass to the axis of rotation, and so we just get our original mr squared from this. That, in other words, the mass that is concentrated right at the axis of rotation has no effect on the moment of inertia. Another way of, like, it doesn't cost any, this is all kind of an approximation, because like if you actually had like a ball like that, like a bowling ball, it does have some rotational inertia because the pieces around it, right? I mean, yeah, if we're spinning a bowling ball around an axis like a globe, clearly the mass is distributed far away from that axis, like it has some shape, but in this case we're approximating these masses to be points. So in the future, I'll make it very clear whether or not there's any approximating going on. but in general, distance is the key. Okay, let's do a little practice with this. So let's combine calculating angular velocity, angular and rotational inertia to calculate angular momentum. So what is the angular momentum of Earth revolving around the sun? We'll do it together. So we need some key information. We know the orbital period, right? It's a year, 365 days. It takes the Earth to go 2 pi around the sun, 1 complete orbit. And then I'm giving us that the mass of the Earth is this, and the distance of the Earth from the sun is this. So now we want to calculate the angular momentum. First, let's go for the rotational inertia. Again, to get angular momentum, we need 2 pieces, rotational mass and rotational velocity. So the rotational mass, or the rotational inertia, I, we get from this summing up of the mr squareds. And here, we're just saying our one mass element is Earth, right? So again, this is showing like kind of an approximation. Earth is, there's a lot of different mass elements that make up Earth, right? But here, Earth is our one chunk, and it's this distance away, and it has this much mass. So we can, it's just that simple mr squared. This is like that one ball on a string is our approximation here. So we just multiply its mass by the distance squared, and we get some moment of inertia I. The units are kilogram meters squared. They're not really intuitive units to think about, but it's important to keep track of them. And now the missing piece is the rotational velocity. So first, what is the direction? Based on how I drew it here, what direction is the angular velocity? Out of the page? We all agree on that? So angular velocity is going to be out of the page. And to figure out what the magnitude is, we just do delta theta over delta t. Like we said, delta theta, if we pick 2 pi, 1 complete rotation, that's a good one to pick because we know that takes a year. So I've just converted 365 days to seconds here. I could also just do 2 pi over 1 year, in which case my units would be different. They would be in inverse years, but whatever. Now I have my 2 desired quantities, rotational inertia and angular velocity. So to get angular momentum, I just multiply them together, and we get some value out of the page, which is very large and doesn't really tell us much, but we were able to solve for it. Any questions about this little example here? Okay, so how do we change angular momentum? Well, just like to change momentum, we need a force. To change angular momentum, we need an angular force, a rotational force, or a torque is what we call it. And they're created by the normal linear forces, pushes and pulls that we've already talked about, right? And let's go back to this handy-dandy chair. If I want to rotate it, I'm going to push part of it, or pull part of it, or something. So like the thing that's causing this chair to rotate is not some like new crazy science concept. It's still a push and a pull, but it's a specific push and a pull. It's a push and a pull to a specific point in a specific direction. And so let's figure out the relationship between that, between the force, the application point, the direction, how those things affect what torque it creates. So like I hinted here, depends on the magnitude and direction. It depends on the normal, the things about force we already know how to describe. But it also depends on where the force is being applied to an object, what torque is made by that force. So let's do a little investigation here. Here's just 4 wheels centered on their axis of rotation, and we're applying 4 different forces to them. And we want to see which one of these will cause the wheel to rotate, just from our experience in the real world. So there's one on the left. If I apply this force like this to a wheel, is that wheel going to spin?
Yeah.
Yeah. Okay, how about the next one? If I apply that force? Yeah. And we also know if these 2 forces are identical, these are probably going to produce the same behavior, right? If I'm trying to spin a wheel, it doesn't matter what side of the wheel I push, right? I'm pushing the wheel in that direction, and so it's going to rotate. So maybe that's looking forward a little bit, but whatever torques these 2 forces create, we probably want that to be the same, right? We don't care that I applied one force up there and one force on the side. All right, number 3, is that going to cause it to rotate? No, that's just pulling on like a bike spoke or something. And yeah, and then that's pulling on the axis. And then number 4, is that going to cause it to rotate? Also no. So I guess a key thing that I didn't point out here, the directions of these two, we know that those won't cause them to rotate, right? If you pull or push on like a different parts of a wheel outward or inward, that's not going to cause it to rotate. But another key, in this third example, I applied a force to the direct center. Can you like think about like a bike wheel or something? If you were going to spin that wheel, can you do so from the exact center? No, you're going to need to push somewhere else. And so we'll talk about why in a sec. But okay, so now we figured out application point and direction of force is clearly important in whether or not it makes a torque. And how do we connect this to torque? Well, the question I asked for each of these was, will this wheel spin? And if it spins, that means we caused a change in angular momentum, right? If we had a still wheel and then we applied a force and then it's rotating, we know that there was a torque because we caused its angular momentum to change. So how do we get the torque from the force? Well, it turns out it is the linear force that is perpendicular to the radial or the vector between the axis of rotation and the application point. So that sounds a lot more complicated than it really is. You just draw a line from where it's rotating from to the force, and you only care about the amount of that force that's perpendicular to it. So if we look in the case of the wheels in the previous slide, right, these first two, the force is completely perpendicular to that radial vector that I drew here, and the force here is completely parallel to it. So the ones that are completely perpendicular, these cause torques, these cause rotations, but when the force is parallel to that radial vector, you get no torque. So we only care about the perpendicular. That's what this little upside down T thing is. It just means perpendicular force to R. But then it also scales with the value of R. So it's F perpendicular times R. And we can see that, you'll see that in DL, like you'll play around with it, but the further away from the center of something, from the axis of rotation that you apply a force, the more torque it creates. Yeah, okay. So, again, the two extremes of this, in this case, F is completely perpendicular to R on the left here. So all of F is making a torque. And on the right, F is not 0, right? We have this blue vector F, and that clearly is a vector with an x component, nothing 0 about it. But the F perpendicular, the amount of this vector that's perpendicular to R is 0. None of that vector F is perpendicular to it. So how do we quantitatively get, if I know my vector F, what's F perpendicular? Like what amount of my vector is perpendicular to R? And the way we do that, unfortunately, is with trig. So in this case, we have a vector that's neither completely perpendicular or completely parallel to this vector R, right? F is diagonal to it. So just like we can break down vectors into x and y components, we can break vectors down into any components we want. Any two perpendicular directions you take, you can describe a vector in terms of how much it is in one and how much it is in the other. And so, and it turns out you can like pick any two perpendicular directions, and that works. But in this case, they happen to be the two directions we're breaking it down into are x and y, because if my r is in the x direction, right, then I can break my f into x and y, and then I only care about the y component, or the perpendicular component, right? You can see my blue vector f, my parallel component on the bottom, my perpendicular component on the right, they're just the normal x and y components that we might identify. But for my torque, we only care about this perpendicular component, in this case the y component of f, and so if I know this angle, I can calculate this as f sine theta for my f perpendicular. So then the torque that this force would create is it's f perpendicular times r, or the magnitude of f times r times sine theta. And of course, this is not always going to be sine. It's sine because in this particular example, the angle I gave is opposite the perpendicular part of the force. But if I gave you this other interior angle on the top, then you would have to use cosine. Right? So you can't just memorize sine is this, cosine is that. You need to know how to apply them. Okay, so I keep saying that we care about the amount of the force that is perpendicular to this r. However, we can also calculate the amount of r that's perpendicular to f. What does that mean, and why would we do it? Well, why would we do it? In this case, it was convenient. My r is already in the x direction, right? So it's easy to break f into the x and y components. That's something we're comfortable with. It's easy to visualize. What if I had a situation like this? So now this is a plank. This pink thing is just like, like a plank rotating. Yeah? Mm-hmm. Yeah, I changed that this morning when I realized the typo. If you downloaded the lecture slides from online that says cosine, it's a typo. Thanks. Okay, so now we have this plank that's rotating, this pink thing, r, and it has a length r, and we're applying a force straight down at the end of it. Now, F, our force, is in a nice vertical y direction that we're comfortable with, and R is diagonal on our page. There's nothing like physically special about that, about like diagonal versus horizontal or something like that. But, we're used to working with a piece of paper that has a sideways direction and a vertical, and I don't know, it just works easier for my brain. So I don't want to mess F up and turn F into this diagonal direction and this diagonal, like two directions that are perpendicular to R. And I could have, but I don't want to. Instead, I can also break R into two components, one that is perpendicular to F and one that is parallel to F. And it turns out that mathematically you're going to get the same answer. If you take the piece of R that's perpendicular to F or the piece of F that's perpendicular to R, in both cases you're just going to have the magnitude of one times the magnitude of the other times some trig function that reduces it by a however amount if they're not completely perpendicular. So that's kind of a cool thing to see about trig functions, is that you can see them as like little modifiers that reduce the vector, because we only want like a piece of it. And in this case, they act as a measure of how perpendicular are these two vectors. And whether I broke F into F perpendicular and F parallel, or I break R, like I've shown here, into R perpendicular and R parallel, that trig component is going to end up being the same thing. So, in this case, the torque created by this vector is F times R perpendicular, or FR cos theta. So again, this is not just like, oh, cos happens when I'm calculating R perpendicular something. It's because I gave us this particular angle theta. In this one case, R perpendicular is R cos theta. But it's always going to be sine or cosine. So whether you use F perpendicular R or FR perpendicular, they're both the same. My general guidance is if one of them is already just vertical or just horizontal, then don't mess it up. Then break the other one up. Break the diagonal one up into X and Y. But it could be neither, right? They could be both horizontal. It's a little more work because then we need to put one into the coordinates of the other. But I guess at the end of the day, the root concept is that there's nothing special about like the X and Y direction we talk about, right? We just need a set of perpendicular axes. And whatever we choose, as long as we use them for the whole problem and we're consistent, it's fine. But again, don't deny your brain that it's much easier for us to think about up and down and side to side. All right, so just a quick summary now of everything we talked about today. Angular velocity, comes from a change in an angle over a change in time. It tells us how fast something is rotating, how long it takes it to go through a rotation. It's a vector. We use the right-hand rule to decide its direction. However, if we want to describe the motion a little more thoroughly, we're going to multiply this omega, our angular velocity, by our rotational mass, or our moment of inertia, or rotational inertia, which has to do with the configuration of the mass and our axis of rotation. So this I is very situation specific, but if we know what the rotational inertia is, then we can multiply it and get our angular momentum, which is a more useful quantity for describing something physically, because it describes how hard it is to get something to rotate, how hard it is to stop it from rotating. And just like when we did collisions, momentum is important because it determines how collisions will play out. How much momentum does something carry when it hits something else? This is a few steps down the line, but we'll get to a point where things are exchanging angular momentum. And so it's important about the relative amounts of momentum and not just how fast they're spinning. And then finally, changes in angular momentum come from torques. And more specifically, the net torque applied over a time causes a change in angular momentum, a delta L. And we can calculate those torques like we just mentioned from the perpendicular amount of the force and the vector that goes from the axis of rotation to the force. Again, when you say it, it's a mouthful, but in reality, where's my axis of rotation? Draw a line from there to where the force is acting, and there's your R vector. So this is the whole story, and all of these all these directions are determined using our right-hand rule. And so that's going to be very valuable. L is in the same direction as omega. Omega is in the same direction as delta theta. And torque and delta L are in the same direction. So I could apply any torque to any object with any angular velocity, but the resulting change, so the angular momentum that we add on to something, is going to be in the direction of the net torque. The last thing I wanted to mention is I know that in DLs right now and for the next day or so, like you're focusing mainly on static systems. So even though today was all about motion and we talked about velocities and momentums and stuff, we start out by calculating a lot of static systems. And what that means is systems where the torque is balanced to 0. So even though I didn't touch on that today, that's something that's important to practice because it gives you a feel for how to actually determine what torques are occurring. Then once we master that, or get more comfortable with it, using this trig, identifying what these torques actually mean, then we'll say, okay, what if they're not balanced? Then we'll get into the motion and kind of go through the same steps that we did for the linear stuff, where we talked about first very simple systems, then let them evolve a little bit, then let them interact with each other. So again, the more comfortable you are with the linear stuff, the better this stuff will go, because the more you can just focus on only the new stuff.